So it's more of a like a geo fantasy combined with a bit of data analysis and how far we are still from actually understanding the geodynamics far away in time. And this is and these are the results that we are showing in a paper that has been published this year. So it's kind of relatively recent. And as you can see here, that there are pictures of people that have collaborated with me on that particular paper. So as we look at the evolution of the understanding of assembly of Australia, or just assembly of different continents through time, it has evolved tremendously, and different models, they actually show you different scenarios, and they are all based on, in some sense, they are based on field observation. Some are based on geophysics, some are based on geochemistry, post reconstructions, and some are just a pure imagination. And then so with that, and it's all fine, because that's the time of the Earth evolution where we are actually allowed to have a lot of imagination at that point. So what we tried to do is to look at the zircons, right? The zircons that are sampled across Australia, and we did it because zircons have really nice superpowers. They are extremely durable and resilient, and with that, they can resist a lot of processes that and things that happen to them. So they are resistant to high temperatures, to metamorphic changes, to high pressures. So with that, they can tell us about what happened when they were created. And also their other superpowers is that they are really good for uranium-lead dating. So with that, we can actually obtain dates of magmatic intrusions or dates of metamorphic processes. And then with that, yes, they are highly resistant, as I managed, that they are extremely stable, and they indicate what the processes that have happened before. So with that, what we've done, we've collected, accumulated all of the samples that were available, let's say a year and a half ago. Of course, those things evolve. And then what we can see here, that we have over 1,000 samples from the Archean magmatisms and much less in terms of metamorphism. In terms of Proterozoic, we have 1,400 and a little and less samples from the metamorphism. And so, but what is interesting here is that those yellow spaces here, that's a sedimentary cover, and that might also tell you about as Mark has asked before, about sampling bias, because we will only sample the areas which are exposed or have been drilled through the younger deposits. So with that, that's the first problem we face, is that to sample the older regions, we need to drill for the younger cover. By any chance they are exposed. And then with that, as you can see here, those dark shapes, these are tectonic provinces about which I'm going to be talking about. They're slightly different from the ones that Lou was showing, because the ones that Lou was showing, they come from Geoscience Australia. These ones are made by Veronica, so they are slightly different, and they are more representative of the tectonic blocks in Proterozoic rather than the whole holistic evolution of Australia. And as you can see here, there are no blocks really in the east, because the east of Australia did not exist at that time yet. It was accreted much later. So the eastern states, they are not part of Australia at that time yet. So as you can see here, all of those different blocks, that they have their names. And then in time, if you plot the amount of samples for every tectonic block, you can see that in some regions you have much denser sampling, while in the other ones you have very sporadic sampling. And what we geologists tend to do is to give names to base our reconstructions, or base our events that happened on very limited data. Because we can't collect them, or it's just that is the amount of samples that we had at the time, and we really want to publish a paper. So just to give you a little bit of an idea what I'll be talking about, every every one of those blocks have a name. We can go A, B, C, D, E, F, G, but we can consider that on in another way. We can actually think about giving them the right names. So if you're a geologist, you know what I'll be talking about. If you are not, just bear with me. So what we're going to start with the Kimberley Craton, and that's going to be our center of the universe for the rest of the talk. And then we have the North Australian Craton that is here with the granite stanamai. Here we have the Albion province that is attached to Northern Australia Craton. Here we have the Southern Australia. Here we have arcs that are in between Western Australia and Southern Australia. Here we have the Western Australia Craton with the Pilbara Craton and the Yilgarn Craton and all of the other orogens that are around. What's important here is that those shapes here, that's going to be that's Antarctica, which at that time was linked with Australia. So therefore we're going to be doing reconstructions with those elements as well. But what you can see here, we have much lessly dense populated sampling in that region. So it can't really come with we can't really make good interpretations based on the data that came from that region. So if we're going to look at those samples in a slightly different way for every block, can I create a variety of different diagrams, and here you have a violin diagram that shows you the distribution of the sampling in time. Here those numbers shows you the amount of samples for particular block. And what we see here, which is very interesting, that we see as some kind of a trend that moves us from, let's say, starting from Kimberley Craton, going clockwise to Western Australia, our samples are generally getting slightly bit younger. And then we can ask our question, but what does it really mean? Okay. And then when we look through the geological literature, there is a whole amount of different orogenies that have been named through the time. And these are the gray shapes here, and they don't always correlate with the zircon data because they might have been interpreted based on tectonics, based on other geological indicators. So you are not really comparing apples with bananas, but I thought it's important to put it on here that some of them, they are based on the geochemistry, but not all of them. And you can see that there's a really large amount of those tectonic events that have been brought up by people, by geologists through the evolution of understanding of Australia. So what we have done is that with the zircon data that we have collected, we have put it into the GPlates, which is a plate reconstruction software developed at the Sydney Uni. And we looked at and we analyzed the models that we are making based on some geodynamical constraints. And I'll give you an example of 3 here. So for example, we know that it takes around from 6 to 10 million years from the onset of the subduction zone before any magmatic arcs are established. So one can take that into account. When there's a termination of subduction by a variety of different processes, in those timeframes, that there's a change of thermal and rheological properties of the slab, and then response in the tectonic above, so on the surface, but we can't really observe that. We can't really see any effects of that on the surface so far in the past. But what is also very, very important is that the point number 3 is that the long-lived subduction systems like Andean system are much more long-lived that small ones like the congested Caribbean style systems, which are potentially living much shorter periods of time because they are composed of much smaller plates that have much shorter lifespan because they get to be subducted much faster. So now I'm just going to show you both models. There are 2 models that are preferential at this moment, let's say in our understanding of Australian assembly, and they all are kind of based on when Western Australia came to meet the rest of Australia. So here we have Western Australia. In this corner, Kimberley Craton, as I said, is the center of our universe. Here we have Northern Australia connected to Southern Australia. So we have Western Australia. So Northern Australia is joining up the Kimberley Craton, and then Western Australia is joining at the time of around 1800. And that red line indicates a potential line of the subduction zone. Here, that nice, really green blob coming in and then out, that would be Laurentia, which would represent part of the Northern America that we know at the moment. And as you can see here, there are certain periods without any blobs popping up, and these are the periods which we don't have any data from. And now everything kind of lights up. So this is a model number 1. There's model number 2, which again, Kimberley Craton is the center of our universe. Northern Australia with Southern Australia coming in together, and then Western Australia is going to join in much later, so around 1300. So it is not part of the Australian system for much longer time. Okay, and what we end up having here is that the Northern Australia joins in, and then we have Andean style subduction happening on the west coast of Northern Australia and Southern Australia coming in together. There's a double sided subduction happening. And Western Australian events, they don't really, they are not really linked to anything that happens within the rest of the Australian Craton during that time. And only around 1300, we end up having an amalgamation of the whole Australia. What we're going to look is that what's important here is that we can discriminate based on the zircon data which one of the models is more probable to happen, and there are pros and cons. So there's a pros for the assembly at the 1800, and it is going to be that there's no magmatism underneath the Kimberley, so this region, and granite stanami after 1700. Right. On the other hand, we definitely can see that there's certain type of Andean style subduction happening at the west coast of Northern and Southern Australia. But what is interesting here is that underneath the Canning Basin here that lies between the Kimberley and then Western Australia Craton, we have no sampling of the older rocks than 1800, which makes you wonder if there was any magmatism taking place, that would indicate that there is a subduction happening at around 1300 of a style of like Andean style subduction coming underneath. And then, as we can see here, when we have a collision of the Western Australia Craton with the rest of the Australia at the earlier stage, so at the 1800, we end up having an internal ocean for 500 million years. And that is a very long period to have such a small basin for such a long time. So with that, we have two models, and both of those models have their pros and their cons, right? And the first question is do we have enough data to actually discriminate and definitely define what model is appropriate to actually understand the assembly of Australia during Proterozoic? Like, how does the younger events bring up the sampling bias? So maybe there have been older events under the Canning Basins, but due to the fact that that there are strong limitations underneath the Canning Basin in terms of sampling, and then there are overprints of the younger events, we are incapable of actually understand that, right? And we see, and with the fact that we see some clear progressive younging of zircons coming back from the Kimberley Craton through the whole margin, internal margin, what does that actually indicate? And the fact that we don't really see the mid-Proterozoic events subduction along the whole coast of the Western Australia Craton, does it mean that there was no long-lived Andean subduction, or we just don't have enough samples. And there I'm going to finish.